Assalamualaikum dear students. I welcome you all to the 11th lecture of Thermodynamics 2. Lecture 11. The contents of lecture 11 are equivalence of Kelvin Planck statement and Clausius statement, violation of Kelvin Planck statement, violation of Clausius statement, perpetual motion machine of third kind, Carnot heat engine, numerical problems, and conceptual questions and answers. Equivalence of Kelvin Planck statement and Clausius statement. Kelvin Planck statement is stated as it is impossible for any device that operates on cycle to receive heat from a single reservoir and produce a net amount of work. Clausius statement is stated as it is impossible to develop a cyclic device which transfer heat from lower temperature to higher temperature without any external energy input. So we have already discussed both these statements individually. Now we will find a relationship between these two statements, Kelvin Planck statement and Clausius statement of second law of thermodynamics. So first we will discuss about the violation of Kelvin Planck statement of second law of thermodynamics. So two thermal energy reservoir, one is at high temperature and second is at low temperature. So high temperature thermal energy reservoir and low temperature thermal energy reservoir, high temperature TH, low temperature TL. So we have a heat engine. So heat function of heat engine is to produce work. So heat engine will receive QH amount of heat from high thermal energy reservoir and reject QL amount of heat into low thermal energy reservoir, and correspondingly the W net amount of work will be produced through heat engine. Now we also have a refrigerator as shown here. So the function of refrigerator is to receive heat from low temperature thermal energy reservoir and eject heat at high temperature thermal energy reservoir. So this refrigerator is receiving QL amount of heat from low temperature thermal energy reservoir and ejecting heat QH into high temperature thermal energy reservoir. So in doing so, we have to perform some work or supply energy, usually in the form of electrical energy, into the refrigerator. Now suppose the net amount of work which was supplied to the refrigerator is less than the net amount of work that was produced by the heat engine. So W net from heat engine is given out and received by the refrigerator, and also the QH amount of heat rejected by the refrigerator is also equal to QH amount of heat that was received by the heat engine. So we have removed that reservoir and connected directly both the points. So the output of refrigerator is the input of heat engine. So QH amount of heat that was rejected by the refrigerator was introduced into the heat engine, and QL amount of heat that was rejected by the heat engine is equivalent to the QL amount of heat that was introduced or obtained by the refrigerator. So we have connected both these points, and the output of heat engine QL amount of heat is the input of refrigerator QL amount of heat. Now violation of Clausius statement. In the previous slide we have discussed about the violation of Kelvin Planck statement, and now we will discuss about the violation of Clausius statement. So we have two thermal energy reservoir TH, that is the thermal energy reservoir that is at high temperature TH, and thermal energy reservoir that is at lower temperature, that is at TL, and we have a heat pump. We know that the function of heat pump is to receive heat from low thermal energy reservoir and eject it into the high energy thermal reservoir. So heat pump is receiving heat QL from low thermal energy reservoir and ejecting it into the high thermal energy reservoir QH. So in doing so, a net amount of work is done on the heat pump. And on the right hand side we have a heat engine. The function of heat engine is to receive heat from high thermal energy reservoir and reject it into the low thermal energy reservoir, and in doing so it will produce a net amount of work done. So our heat engine is receiving QH amount of heat from high thermal energy reservoir and ejecting QL amount of heat into low thermal energy reservoir, and a net amount of work output is obtained. Now the heat engine that was producing W net is equal to the work needed by the heat pump. So the output of work from the heat engine will be input of the work of heat pump. QH is the amount of heat that was rejected by heat pump into the high thermal energy reservoir, and QH is also the amount of heat that was received by heat engine from high thermal energy reservoir. Therefore the heat pump QH will be equal to the QH of heat engine, and heat engine is rejecting QL amount of heat into low thermal energy reservoir, whereas QL is the same amount of heat that was received by heat pump through low thermal energy reservoir. Therefore the output of heat engine QL is equal to the input of heat pump QL. So here is a note: any device that violates Clausius statement also violates Kelvin Planck statement. So we have to remember what was the Kelvin Planck statement and Clausius statement. One said that it is impossible, as you can see that there is no thermal energy reservoir to eject heat, so and no net amount of work is done. So both the devices or schematics that were on the previous slide and on this slide, so in the previous slide that violates the Kelvin Planck statement, and in this slide violation of Clausius statement. So any device that violates Clausius statement also violates Kelvin Planck statement. Any device that violates Kelvin Planck statement also violates Clausius statement, and any device that violates Clausius statements also violates Kelvin Planck statement. Therefore Kelvin Planck statement is equal to Clausius statement. These two statements are known as the parallel statements of second law of thermodynamics. perpetual motion machine of third kind. So, perpetual motion machine of third kind is a device which will work continuously without exchanging energy as heat or work from surrounding. So, the devices which were obtained on the previous slide when we were talking about the equivalence of Kelvin Planck statement and Clausius statement was in the form of perpetual motion machine of third kind, because they were continuously exchanging energy as heat or work from surrounding. So as the low thermal energy reservoir and high thermal energy reservoir was removed, so they were producing work continuously without exchanging energy as heat or work from surrounding. This machine is internally reversible as well as externally reversible. So now we will discuss what is internally reversible mean and what is externally reversible mean and what is totally reversible mean. So a process is called internally reversible if no irreversibility occurs within the boundary of system during the process. So all the element and process inside the boundary will come into the equilibrium and there is no irreversibility left. A process is called externally reversible if no irreversibility occur outside the system boundary during the process. So as you know that outside the boundary means in the surrounding. So as the process is occurred, there is no irreversibility in the surrounding. So all the during the process and at the end of the process, there is no irreversibility left in the surrounding. And a process is called totally reversible or simply reversible if it involves no irreversibility within a system or its surrounding during the process. So a process is said to be totally reversible if it is internally reversible as well as externally reversible. So back to the perpetual motion machine of third kind. The third point states that this machine does not violate either first law of thermodynamics or second law of thermodynamics. So as you can remember from the previous slide, so when we removed the thermal energy reservoir one by one, initially we removed the thermal energy reservoir, the source and then the sink. So you can see that neither of that violates first law of thermodynamics or second law of thermodynamics. This machine is theoretically possible but practically not possible due to the presence of friction. So in the whole scenario we are neglecting the condition of friction. So as we are neglecting the friction, so therefore the perpetual motion machine of third kind is theoretically possible but not practical. So you can see on the left hand side we have a heat engine and on the right hand side we have a heat pump. So the function of heat engine is to receive heat from high temperature thermal energy reservoir and reject heat at low thermal energy reservoir. So QH is the amount of heat a heat engine is receiving from high temperature thermal energy reservoir and QL is the amount of heat engine is rejecting to low temperature thermal energy reservoir. And on the right hand side we have a heat pump. So the function of heat pump is to receive heat from low temperature thermal energy reservoir and reject heat into high temperature thermal energy reservoir. So heat pump is receiving QL amount of heat from low temperature thermal energy reservoir and rejecting QH amount of heat into high temperature thermal energy reservoir. So the output of heat engine QL is equal to the amount of heat that is received by the heat pump QL from low temperature thermal energy reservoir. Therefore, we have joined these points. So output of heat engine is equal to the input of heat pump, whereas QH amount of heat received by heat engine from high temperature thermal energy reservoir is equal to the amount of heat QH rejected by heat pump into the high temperature thermal energy reservoir. Therefore, we have joined these points as well. Now you can see that this is a perpetual motion machine of third kind. So an amount of work is done, but there is no thermal energy reservoir involved, and there is no exchange of energy in the form of heat or work from the surrounding. So this machine is theoretically possible. It does not violate either first law of thermodynamics or second law of thermodynamics, but this machine is practically impossible due to the presence of friction. So the next topic is Carnot heat engine. So Nicolas Leonard Sadi Carnot was a French mechanical engineer. He proposed this model of heat engine in 1824. This engine is named after him, Carnot heat engine. It is the best known reversible cycle. So we will discuss the cycles that are involved in Carnot heat engine. So the first point is, it is the best known reversible cycle. So Carnot heat engine is a reversible cycle heat engine. It is composed of 4 reversible processes. So process 1 is reversible isothermal expansion, in which we add heat. So it is concluded as heat addition. Second process is reversible adiabatic expansion. Third process is reversible isothermal compression, and heat is rejected during this process. Therefore, we have written heat rejection in the bracket. And fourth process is reversible adiabatic compression. So this is a cyclic process, and all these processes are reversible as well. So the note is, any device that follow reversible process can achieve highest efficiency. So if we have two devices, one device operates on reversible processes and the other operates on irreversible processes, then the device which operates on reversible process will have highest efficiency or greater efficiency than the device which operates on irreversible process. Example: motion of frictionless pendulum. So as the name suggests, frictionless, therefore the effect of friction will be neglected or absent. Therefore the motion of pendulum without friction is the example of reversible process. Frictionless piston and cylinder. So as you know that there is a friction involved when there is a mechanical motion. So during the motion of piston cylinder, when a piston is moving inside the cylinder, so there naturally there is a friction involved, but theoretically when we are solving our problems we neglect the effect of friction. Therefore the process frictionless piston and cylinder, the motion is said to be reversible process. Heat transfer through infinitesimal temperature or pressure difference. So if we have to transfer heat from very small temperature difference, for example we have to transfer heat from 20 degrees centigrade to 19.999 temperature degree centigrade, so that difference is very small. So the heat transfer between these 2 points will be a reversible process. Or we have to transfer fluid or liquid from a pressure of 200 megapascal to 2.00001 megapascal. So the pressure difference between these 2 points will be very small. So these process is said to be a reversible process. So the first process is reversible isothermal expansion. Now we are studying Carnot heat engine process one by one. So we will discuss first process, reversible isothermal expansion, that is heat addition. So you can see Q2 amount of heat is added to the system. So in gray color that is a piston, and in yellow color that is the substance. So the isothermal suggests that during the process the temperature will remain constant. So expansion suggests that the increase in the volume, and heat addition means that Q2 amount of heat is added to the system. So from first law of thermodynamics, Q12 is equal to U2 minus U1 plus W12. So U2 minus U1 is the change in the internal energy. So for ideal gas, the internal energy is a function of temperature. So in isothermal process, the temperature difference is 0 because it's a constant temperature process. Therefore, for ideal gas, delta U will be equal to 0. Therefore, W12 is equal to Q12, and the entropy is equal to change in entropy is given by Q by T. So as T is the constant value, any specific constant value, so Q is the amount of heat added. So Q will be positive. So that's why del S will also be positive value. So this shows that there will be an increase in the entropy of the system. Second process of Carnot heat engine, that is reversible adiabatic expansion. So reversible adiabatic process is also an isentropic process, that is written in the inside the bracket isentropic process. And expansion suggests that the volume will increase and piston will move upward, and adiabatic suggests that there is no heat enter or leaves the system. So from first law of thermodynamics, Q23 is equal to U23 plus W23. So as the adiabatic process is mentioned, so Q is equal to 0 and W23 is equal to minus U23. The negative sign of internal energy change shows there is decrease in internal energy and consequently temperature will also decrease. So you know that as this is an expansion process and temperature and pressure are inversely proportional to each other. So as pressure, so temperature and volume are inversely proportional to each other. So as volume is increasing, therefore temperature will decrease because that is an adiabatic process and no heat is entering into the system. So volume will increase and temperature will decrease, and U23, that is the internal energy, will also decrease. Third process of Carnot heat engine cycle, that is reversible isothermal compression, that is heat rejection. So heat is rejected during this process, so heat rejection is mentioned in the inside the bracket. So isothermal means that the temperature throughout the process will remain constant. Compression means the piston will move downward and volume will decrease. And heat rejection suggests that Q1 amount of heat will be rejected to the ambient air surrounding. So from first law of thermodynamics, del Q is equal to del U plus del W. So isothermal, therefore U will be cancelled out and Q will be equal to minus W34. So as Q is the amount of heat rejected to the surrounding, therefore the total energy content of the system will be reduced, therefore a minus sign is shown. So from the relation of entropy del S is equal to Q by T, the negative sign shows that entropy of the system is decreasing. Fourth process of Carnot heat engine cycle, that is reversible adiabatic compression. So as a reversible adiabatic process, this is also an isentropic process as well. So adiabatic suggests that there will be no heat enter or leave the system. Compression means that piston will move downward and volume will also reduced. And isentropic suggests that the entropy of the system will remain constant. So from first law of thermodynamics, del Q is equal to del U plus del W. So as no heat enter or leave the system, adiabatic process, so Q will be 0 and U14 plus minus W14. So internal energy is equal to the amount of work done. So del S is equal to minus Q by T. So Q is equal to 0, therefore S is equal to 0. So it suggests that reversible adiabatic process is also an isentropic process. That is also proved here. So note says that increase in internal energy means that the temperature will also increase. So here U14 is a positive value, that means the temperature of the system will increase. So as you know that temperature and volume are inversely proportional to each other. As volume is reducing, therefore temperature will be increasing. So here all four processes that we have discussed individually are shown on the PV diagram collectively. So here you can see from 1 to 2 the process isothermal expansion or heat addition is also involved in the 1 to 2 process, and 2 to 3 adiabatic expansion. From 3 to 4 isothermal compression, and from 4 to 1 adiabatic compression. So in the PV diagram you will see a green line that show from process 1 to 2, and QH is the amount of heat added during the process 1 to 2. So as the process is isothermal, so TH is equal to constant. So TH temperature will remain constant from process 1 to 2, and from process 2 to 3, that is adiabatic expansion. So you see that volume is increasing in process 1 to 2 and 2 to 3, the volume is increasing. So this is adiabatic expansion, so no heat enter or leave the system. So for process 3 to 4, you will see that in indigo color line, so that is isothermal compression. This is also known as heat rejection process. So in process 3 to 4, QL amount of heat is rejected into the atmosphere, and the temperature will also remain constant from process 3 to 4. So the temperature is TL. So TL will remain constant from 3 to 4. And for process 4 to 1, light blue color line is shown. So process 4 to 1 is adiabatic compression. So you see that pressure is increasing, whereas volume is also decreasing from process 4 to 1. So that is a PV diagram of Carnot heat engine cycles. Now a comparison of PV diagram with TS diagram is shown for Carnot's engine cycle for individual state as well. So you will see in state 1, that is isothermal expansion. State 1 to 2, process 1 or process 1 to 2 is an isothermal expansion, and Q2 amount of heat is added. So 1 to 2 in PV diagram, we have also already discussed this in the previous slide as well. In PV diagram, from 1 to 2, a Q2 amount of heat is added, and this is an isothermal process, so temperature of the system will remain constant. Q2 amount of heat is added and volume is increased. So as this is the isothermal process, temperature remain constant. When we see this same process on the TS diagram, so in TS diagram from 1 to 2, that is a straight line because temperature is constant. From 1 to 2, red arrow suggests that heat is added in this during this process. So 1 to 2, heat is added but temperature remain constant, whereas entropy is increased. In process 2 to 3, that is adiabatic expansion. So 2 to 3, that is also a power stroke, adiabatic expansion. So we know that reversible adiabatic process is isentropic process in which entropy remain constant. So when we see process 2 to 3 on TS diagram, we see a straight vertical line. From 2 to 3, a straight line that suggests that entropy remains constant. For process 3 to 4, that is isothermal compression, and Q1 amount of heat is rejected to the atmosphere. So in PV diagram, in light blue line color line, you will see that 3 to 4, that is a exhaust stroke. So heat is rejected to the atmosphere. And when we see the corresponding process 3 to 4 on TS diagram, so that is a isothermal compression. Therefore, due to isothermal process, the process of 3 to 4 is a straight line in the temperature. So temperature from the process 3 to 4 remain constant. And for process 4 to 1 is an adiabatic compression. So on PV diagram, when we see process 4 to 1, that is an adiabatic compression. So when we see process 4 to 1 on TS diagram, reversible adiabatic process is also an isentropic process. Therefore, from process 4 to 1 is also a straight line. So this is a Carnot heat engine. Cycles, all these cycles are individually showed on the upper side. On the left hand side, bottom side, you can see PV diagram, and on the right hand bottom side you will see a TS diagram showing all these cycles individually. Why Carnot heat engine is impracticable? Because it is impossible to perform frictionless process, impossible to transfer heat without temperature difference, or impossible to transfer heat with negligible temperature difference. Isothermal process can be achieved only if the piston moves very slowly to allow heat transfer so that temperature remains constant. Adiabatic process can be achieved only if the piston moves as fast as possible so that heat transfer is negligible due to very short time available. So as you know that in the Carnot heat engine we have 4 cycles, 2 of them comprises of isothermal processes and 2 are reversible adiabatic process. So for reversible isothermal process, the system must be perform that process very slowly, whereas for adiabatic process the process must be performed very fast. So as we have neglected the frictional effect are also neglected, and temperature difference, with very small temperature difference heat transfer and isothermal process should be performed very slowly, and adiabatic process should be performed very fast. Therefore all these are the reason behind that Carnot heat engine is impracticable. So the question arises, why then, if the Carnot heat engine is impracticable, then why should we study Carnot cycle? So the answer is, the efficiency of actual cycle or heat engine can be improved by attempting to approximate the Carnot cycle more closely. So as you know that Carnot heat engine or Carnot cycle has the maximum efficiency. We study the Carnot heat engine cycle so that when we are performing our calculation for real engine, so we should copy that or try to approximate or get more closer to the efficiency to the Carnot heat engine. So for the real engine or actual cycle, we should improve our efficiency by approximating or by getting closer to the Carnot cycle. Conceptual questions. Does a process become more or less reversible with respect to heat transfer if it is fast rather than slow? So answer is, if the higher heat transfer rate is caused by larger delta T or change in temperature, then the process is more irreversible. So as the process would be slow due to lower delta T or temperature difference, then it approaches a reversible process. So it suggests that if we have a heat transfer from a temperature difference that is greater, let's suppose we have a heat transfer from 500 degrees centigrade to 200 degrees centigrade temperature difference, will be a heat transfer. And in the second scenario, we have a heat transfer between 500 degrees centigrade and 500.001 degrees centigrade. There will also be a heat transfer, but the later would have be more close to the reversible process. So the delta T or temperature difference defines the reversibility or irreversibility of the process. Conceptual question. Geothermal underground hot water or steam can be used to generate electric power. Does that violate the second law? Answer is no. Since the earth is not uniform, we consider the hot water or steam supply as coming from one energy source. So source will have a temperature that is high, and we must reject heat to low temperature reservoir as the ocean or lake or the atmosphere, which is another energy reservoir. So as you can see in the diagram, so there are certain portion or region on the earth which eject heat in the form of hot stream. So Iceland uses a significant amount of steam to heat building and to generate electricity. So that is a geographical contribution of the earth, that in certain region it eject heat in the form of steam. So that portion will become a high temperature reservoir. So we can install a heat engine over here or a work producing device, and we will reject heat into the atmosphere that will act as a low temperature thermal energy reservoir. So it does not violate second law of thermodynamics. Conceptual question. Two heat engines operate between the two same reservoirs and both receive the same QH. One engine is reversible and the other is not. What can you say about the two QLs? So I have already discussed about regarding the efficiency of a reversible and irreversible heat engine. If you have two thermal energy reservoirs and both operates on the same temperature level, then the efficiency of a heat engine that is reversible will have a greater efficiency. The reversible heat engine can produce more work. That means the reversible heat engine is more efficient than the irreversible heat engine. So irreversible heat engine will be less efficient, and due to the energy conservation, it then gives out a smaller QL compared to irreversible heat engine. So W reversible is equal to QH minus QL reversible, and W reversible will be greater than W irreversible. So formula for both W is QH minus QL. So QL reversible will be less than QL irreversible. So you have to decrease the temperature. The temperature of low thermal energy reservoir will be lesser. Conceptual question. Compare two domestic heat pumps A and B running with the same work input. If A is better than B, which one heats the house most? So as you know that the function of heat pump is to take heat from low thermal energy reservoir and reject heat in the high temperature thermal energy reservoir. So they are used to heat the house, and in the question we have asked to compare two domestic heat pumps running with the same work input. So the work input or energy input is same for both. So the statement that A is better than B means that A has a higher coefficient of performance, and since QH of A is equal to QH of coefficient of performance of A heat pump into W is greater than QHB is equal to coefficient of performance of BW. Thus, it provides more heat to the house. Numerical problem. Statement is given as an automobile engine produces 136 horsepower on the output shaft with thermal efficiency of 30%. The fuel it burns gives 35,000 kilojoule per kg as energy release. Find the total rate of energy rejected to the ambient and the rate of fuel consumption in kg per second. So first of all, the power is given to us in the statement is in horsepower. We have converted it into kilowatts. So that is a formula to convert horsepower into kilowatt. And Q dot H or rate of heat transfer is W dot divided by efficiency. So W dot we have calculated in the previous step in kilowatts, and 30% efficiency is given to us in the statement. Therefore, rate of heat transfer comes out to be 333 kilowatt. The energy equation for the overall engine gives Q dot L is equal to Q dot H minus W dot. So we have all the values on the right hand side. Therefore, rate of heat transfer at the lower temperature thermal energy reservoir is 233 kilowatt. From the energy released in the burning, we have Q dot H is equal to M dot QH. So small qh is the specific heat. So the mass flow rate comes out to be M dot is equal to Q dot H divided by small qh, and mass flow rate is 0.0095 kg per second. Numerical problem power plant. A coal-fired power plant has an efficiency of 35% and produces net 500 megawatt of electricity. Coal releases 25,000 kilojoule per kg as it burns. So, how much coal is used per hour? From the definition of the thermal energy and energy released by the combustion called heating value, we get as you know that the formula for efficiency is W dot over Q dot H or W over H. Therefore, W dot is efficiency into Q dot H, and Q dot H is replaced by M dot into heating value. HV is the heating value. So that heating value depends upon the quality of coal. So if we have a good quality coal, then it will release a larger amount of heat per kg. If we have a poor quality coal available, then let's suppose the coal that is given to us in the statement is good quality coal. It releases 25,000 kilojoule of energy per kg, and if we have a poor quality coal, then it might release 10,000 kilojoule of energy per kg. So M dot is equal to W dot over efficiency into heating value. So we have all the values on the right hand side. Therefore, M dot is equal to 57.14 kg per second. So we will multiply this term to convert into R with 60. We have 60 into 60, so 3600. When we multiply 57.14 into 3600, we have mass flow rate in kilogram per hour. So lecture 11, home assignment. All students are advised to go through example problems of each topic discussed in this lecture. So you should go into your textbook and go through all the example problem for each topic. All students must submit handwritten lecture summary report minimum of 3 pages before the commencement of next lecture. All students are advised to submit hard copies of every assignment and report. All students are advised to prepare previous lecture thoroughly before the next class, as there will be a viva or oral answer question session for every student. Thank you very much.